What we want to do here is look at other factors that could come into our scatter plot that aren't as clearly evident just on our original scatter plot. So what this is introducing are some other conditions that we should really think about before analyzing correlation or that coefficient of determination or this equation of the line. Before we do any of that to create analysis for our data, we should be careful of these other factors that could be coming in. So one piece is lurking variables. So what we have here is a graph showing TVs per 1,000 people and life expectancy. And from our correlation coefficient, what we could see is that this is a moderate strength and it's positive. So what that's telling us is that as the TVs per 1,000 people increases, life expectancy increases. So like this bundle up here, France, Japan, Canada, UK, and the United States, these have high life expectancies and also high numbers of TVs per 1,000 people. And then as we decrease the number of TVs per 1,000 people, life expectancy decreases as well. Now, seeing this association, it's relating two variables and you can absolutely graph them together, but there's a piece missing. So if someone saw this graph and said, "Oh, I'm going to go out and buy a bunch of TVs because then I'll live longer," doesn't quite work that way. It isn't, again, we can't say cause and effect, but also it's not necessarily the TVs that are creating this longer life expectancy. So we could think of are some other variables that would be at play here. If there are more TVs in the country, that typically relates to a more developed country. So it could just deal with development, which leads to usually better healthcare, usually more technology available. And with those different pieces comes kind of better surgical equipment, better just various pieces of equipment to increase life expectancy. So with that, while we're able to graph TVs per 1,000 people and life expectancy, it's not necessarily those two things relating. It's this lurking variable of just overall development of the country and how that affects life expectancy. So be careful of lurking variables. Another thing we can look at is residual plots. So in this first one, we have these two graphs that are going to relate to each other. It's taking the scatter plot and changing into a residual plot. What it does is it takes the equation for the line that you get out, that line of best fit, and basically makes it a horizontal line in the residual plot graph. And that residual plot graph, that line, represents the idea of zero. Because remember with residuals, if you have a value that lands exactly on the line, then that value has a residual of 0. And then anything that lands above is a positive residual, anything that lands below is a negative residual. So like to follow a coordinate here, like this one point on the scatter plot that's just slightly below the line there, which would mean it's making a slightly negative residual. On the residual plot, that's coming through as this point right here. So it would line up as the same x-coordinate. It's just in terms of placement, it stays just a little bit below the line. What's nice about the residual plots is sometimes things that weren't clear before in the scatter plot become clear in the residual plot. Things like outliers or trends become more obvious. Now, what we want to see in the residual plot, and this first example is a fantastic scatter plot. This is what we'd want to see from a strong linear association. It's the idea that most values are close by the line in the scatter plot, which will come through as most values close to the line in the residual plot. And then while values can kind of scatter away from that line, there shouldn't be many values away from the line. So what we want to see in residual plots is most of our values close by, and then it should decrease as we move away. And that description right there is the description of a bell-shaped curve. We basically want to see a bell-shaped curve kind of vertically here, where we have a high probability of landing in the middle, and then that probability decreases as we move further away from the line. So we want to see this kind of normal distribution of our residuals. For the second scatter plot, where this could look pretty linear in our scatter plot, and we did even make a line through it, in the residual plot, we can see this clear curve coming through. There's an obvious curve, and with that, it becomes a little more obvious that there was curving in the original scatter plot. It's just a little hard to see. So with this is not a form that we would want to use. If we saw this in our residual plot, we would not want to make the equation of the line because it's not actually linear. The data would be curved. Then in this last case, looking at the scatter plot, it looks very weak, but maybe it's linear. But what we could do is see that if you look at the residual plot, it wouldn't be normally distributed. It kind of would be a uniform distribution in terms of probability and everything being equally probable. That landing close to the line has the same frequency as landing further away from the line. So we also wouldn't want to work with this last case because there's just no linear pattern to it. So to make residual plots, if we're in GeoGebra, if you're at the scatter plot here, what you can do is change from scatter plot to residual plot. So like this is our airline data. And this will just show, yep, most values are landing near the line, probability decreases. We might want to look into this value here, which happens to be Miami. Since it has such a large residual, maybe that's an outlier. It becomes a little clearer in this form than in the scatter plot. So with that, we'd want to check this and just make sure that those residuals are roughly normally distributed. Down below here, we have our cricket data. Again, we could even look at what if we separated up this data and looked at the frequencies. So in terms of frequencies, like there's 3 values in that range, 1, 2, 3, 4, 5 values in this range, 1, 2, 3, 4 values in this range, and 3 here. This idea of kind of increasing towards the middle and then decreasing as we move out is exactly what we want to see. So in terms of looking at the equation of the line, we're all good to go there. So this just introduces some conditions that we should check for residuals. We want to avoid any bends or other patterns coming from the residual plot. We want to check out any outliers that become clearer in the residual plot. And then look for any change in variability, which in terms of on a residual plot, what that would look like is if everything was close by at the beginning and then started spreading out, usually makes kind of a tornado shape like that. That's something we want to be careful of. We kind of want consistent variability. Like we see down here with the cricket data is it's always pretty evenly scattered, moving above and below that line. That's perfect. So those are some other features we can look at with our scatter plots.